Hey there, welcome back to Graph Theory. In this video, we're going to focus on graphs and their adjacency matrices. In particular, we'll discuss how to find all of the eigenvalues of a given adjacency matrix for nice families of graphs. To recap, a graph is an ordered pair G equals V comma E, where V is a set called the vertices of G, and E is a set of subsets of V of size 2 called the edges of G. When we discuss graphs, it's helpful to keep a standard example in mind, the example of a social network. In a social network, the users in that network are the vertices of the graph. The relationships between users, for example, friend connections in a social network, are the edges of the graph. And these edges in a graph are undirected. In the videos last week, we talked about a few different examples of matrices that you can define based on a given graph or digraph, where again, digraph is a shorthand for directed graph. So one of the matrices that we saw was the adjacency matrix, which is defined for graphs. Some other matrices that we saw, which were defined for digraphs, are the random walk matrix and the lazy random walk matrix. These are matrices that we used in the PageRank algorithm, which we implemented for some small digraphs in the last video. I'll also mention that both the random walk matrix and the lazy random walk matrix can be defined for graphs as well as digraphs. And like I said, we use those matrices in PageRank, so they are very useful in real-world applications. Today, instead of focusing on digraphs, we're going to focus on graphs, the undirected graphs. And specifically, we'll look at techniques for finding all of the eigenvalues of their adjacency matrices when the graphs are especially nice. In order to look at the eigenvalues of adjacency matrices, let's review what the adjacency matrix actually is. So given some graph G of order n, in other words, the graph has n total vertices, and the vertices are named v1, v2 up to vn, we define the adjacency matrix of that graph, which we denote A sub G, as the n by n matrix whose ij entry is equal to 1 if and only if the vertices vi and vj are adjacent in G. And otherwise, we set the ij entry equal to 0. One thing to note is that in an undirected graph, if there's an edge ij, there's also edge ji, and vice versa. So if we have a 1 entry at ij, we must also have a 1 entry at ji, and vice versa. And this tells us that our adjacency matrix is always going to be symmetric, regardless of the graph. Which means, if we want to know about the eigenvalues, all of those eigenvalues of the adjacency matrix have to be real, because the matrix is symmetric. And we saw in last week's videos that the eigenvalues of the adjacency matrix are useful, not just because it's interesting to see what eigenvalues are, but because they tell us information about the structure of the graph, whose adjacency matrix we find the eigenvalues of. So for example, one of the problems that I put in last week's video was to prove a bound on the maximum eigenvalue of the adjacency matrix in terms of the maximum degree of the graph. So given the maximum eigenvalue, we can determine information about the maximum degree, and vice versa, because we have this bound. And this is not the only example of information that we can gain about the graph or the matrix, given information about the other one. And we'll see more examples like that in the future. Today, we're going to see a couple of examples of nice families of graphs and how we can find all of their eigenvalues using some simple techniques. Our first example will be the family of complete graphs. For example, if we look at the complete graph of order 5, here is its adjacency matrix. That adjacency matrix, we can describe it in words as having all ones except for zeros on the diagonal. So we noted in last week's videos that this adjacency matrix in the n equals 5 case has an eigenvalue of 4, and a corresponding eigenvector for that eigenvalue is the all ones eigenvector. In general, if we have a matrix where all of the row sums are the same, we'll always have that eigenvector, the all ones eigenvector, and the eigenvalue for that eigenvector will be the row sum. So this is why we see regular graphs, if they're k-regular, having an eigenvalue of k, with the corresponding eigenvector being an all ones eigenvector. In more generality, if we're looking at the complete graph k sub n for any n, we can conclude that it has an eigenvalue of n minus 1, for the same reason why we concluded that the n equals 5 example has an eigenvalue of 4. It's because the row sum is going to be n minus 1 of the adjacency matrix of k sub n. And the vector with all ones is going to have an eigenvalue equal to n minus 1 when we multiply the matrix times that vector. So we're able to find one eigenvalue already. We know that n minus 1 is an eigenvalue of the adjacency matrix of the complete graph of order n. The problem, though, is that there are a total of n eigenvalues, and we only know one of them. So we have n minus 1 others that we need to find. How can we find those other eigenvalues? Well, there's some useful facts from linear algebra that we can combine, and they will help us find the rest of the eigenvalues. And like I said, there's a total of n eigenvalues. It's possible that some of them are repeated, though. So there's n of them with multiplicity, but we don't know how many of them are distinct. So we're going to use some useful facts. The first fact is that if you have a square matrix A, the rank of that matrix is the same as the number of non-zero eigenvalues with multiplicity. Another useful fact is that if we have an n by n matrix A, then lambda is going to be an eigenvalue of A if and only if lambda minus k is an eigenvalue of A minus k times the identity matrix. And the identity matrix that we're using, of course, has the same dimensions as A. And this second fact can be seen right away from the definition of eigenvalue. In order to find all the eigenvalues of the adjacency matrix of the complete graph of order n, we're going to define a graph that looks a little bit like it, but it's going to be different on the diagonal. This graph is going to be called J sub n, where n denotes the side length of J, and it's just the n by n all ones matrix. So the n by n all ones matrix only differs from the adjacency matrix of Kn on the diagonal, because the all ones matrix has ones on the diagonal, but the adjacency matrix of the complete graph has zeros on the diagonal. Since all of the rows of Jn are the same, and all of these rows are non-zero, we can conclude that the dimension of the row space of Jn is 1. And the definition of rank is the dimension of the row space. So the rank of Jn is 1. Now we can use that linear algebra fact in the second bullet. The rank of a matrix is equal to the number of non-zero eigenvalues. So if J has rank of 1, that means that J has exactly one non-zero eigenvalue. And that also means, since there's only one non-zero eigenvalue, all of the other eigenvalues have to be 0. J has a total of n eigenvalues because J is an n by n matrix. That means that we have eigenvalue 0 with multiplicity n minus 1. As for the non-zero eigenvalue, we see that our matrix J is similar in a way to the adjacency matrix of the complete graph of order n because the matrix J has the same row sum in every row. That tells us that the all ones vector is an eigenvector of J, and the eigenvalue of the all ones vector for J is going to be n. So that n is the non-zero eigenvalue of J. So the eigenvalues of J, J sub n, are n with multiplicity 1 and 0 with multiplicity n minus 1. And that's what I've written in that top bullet. And now we're going to use the other fact from linear algebra, the one that just follows straight from the definition of eigenvalues. In order to use that fact, we'll write the adjacency matrix of Kn in terms of Jn. So like we said before, the only difference between these matrices happens on the diagonal. So we can say that the adjacency matrix of the complete graph of order n is equal to J minus I, where J is the all ones matrix with the same dimensions as the adjacency matrix, and I is the identity matrix with the same dimensions as the adjacency matrix. Note that J minus I is the same as J minus 1 times I. So we can conclude that all of the eigenvalues of the adjacency matrix of the complete graph of order n are 1 less than all the eigenvalues of J. And we already found the eigenvalues of J. So now we can take each of those eigenvalues, subtract 1 from them, and that will give us the eigenvalues for the adjacency matrix. In other words, the adjacency matrix of the complete graph of order n has the eigenvalue n minus 1 with multiplicity 1 and minus 1 with multiplicity n minus 1. Now let's move on to the next case. In this case, we'll still use that fact about the rank, but we're going to have to do something a little different after that. So here we're going to look at a star. Again, I'll draw a picture of an adjacency matrix for a star that has order 5, but it's going to be a different matrix because the graph is no longer complete. So a lot of the ones have now become zeros. The way I drew my star, I assume that V1 is the center. So V1 has edges to all the other vertices, V2, V3, V4, V5, and there's no edges from V2, V3, V4, V5 to any of each other. So they only have edges to V1. So they're all leaves except for V1. When we look at that matrix, we can see pretty easily right away that there's an eigenvalue of 0. And there's a lot of choices we can make for a corresponding eigenvector for the eigenvalue 0. So here's one example. Eigenvalue 0, we can take a corresponding eigenvector of 0, 1, minus 1, 1, minus 1. So let's look at that for a second. If we take that vector and we multiply it on the right with the matrix on the left, so the first entry we get in the product, this is going to be the dot product of the first row of the matrix with the vector. And that's going to give us 0 for the first term in the dot product. Then we're going to get a 1, a minus 1, a 1, minus 1. We add them together, we get a 0. So the 1s and minus 1s cancel. The rest of the entries in the product are going to be obtained by taking the dot products of the second, third, and fourth rows of the matrix with the vector. And as you see, when you take those dot products, you get 0 for all of them. So all the terms have zeros in the product. So everything gets zeroed out, and this gives us an eigenvalue of 0. So it's pretty easy to see that 0 will be an eigenvalue. In fact, it's pretty easy to see that 0 will be an eigenvalue with multiplicity higher than 1. But that doesn't really give us what we want. We want to know all the eigenvalues, and trying to think about it this way seems less direct than trying to use some useful facts. So let's resort to the facts. So one fact, like I said, that we'll use is the rank again. And if we want to use the rank, we can see that this matrix has a lot of repeated rows. So in particular, all of the rows of this adjacency matrix, except the first row, are the same as each other. So rows 2, 3, 4, and 5 are all the same. And in general, for k1n, rows 2, 3, 4, all the way up to n plus 1 will all be the same. Thus, we can conclude that the rank of this adjacency matrix has to be 2, because there are 2 distinct non-zero rows. These non-zero rows are not multiples of each other. So the first and second rows, they're non-zero and they're not multiples of each other. And the second through n plus first rows are all the same as each other. So the rank is at most 2, and the rank is at least 2. It has to be equal to 2. And that tells us that there must be exactly 2 non-zero eigenvalues of this adjacency matrix. So we can conclude that 0 is an eigenvalue with multiplicity n minus 1, because the total number of eigenvalues is n plus 1, because the adjacency matrix of the star k1n has side lengths of length n plus 1. So we need to find those 2 non-zero eigenvalues. We can use another fact from linear algebra, which will give us some more information about those eigenvalues. So this is related to the trace. And the trace of a square matrix A, which we denote TR of A, is just the sum of the diagonal entries of A. And the fact that we're going to use is that the sum of the eigenvalues of A is the same as the trace of A. So if we look at the trace of our adjacency matrix, we can see that it's 0. So by definition of the adjacency matrix, the trace will always be 0. So this tells us that the sum of the eigenvalues of our adjacency matrix must also be 0. Now, we also concluded that there are only 2 non-zero eigenvalues. So that means that the sum of those 2 non-zero eigenvalues must be 0. And what does that mean? Well, by definition, it means that those 2 non-zero eigenvalues are going to be additive inverses. So now, let's find those non-zero eigenvalues. And this technique that we'll use to find them is something that works a lot of the time. And it might seem like it shouldn't usually work, but the only reason it's working is because these adjacency matrices are so nice. So what we're going to try to do is we're going to try to guess what the eigenvector should look like. And then we'll try to solve for an eigenvector and the eigenvalues. So in particular, we'll look at the structure of our adjacency matrix, and we're going to try to guess what the general form of the eigenvector should look like based on the matrix structure. We'll plug in this form for the eigenvector that we're guessing should be right. We'll see what we get when we multiply the adjacency matrix times the eigenvector, and then we'll solve for the parameters in this eigenvector to figure out what the eigenvector should be and what the eigenvalue should be, assuming that our form that we guessed actually gives us a valid eigenvector. If we don't guess a good form, we won't find a good eigenvector, we won't find an eigenvalue. If we guess a form that makes sense based on the structure of our matrix, this will actually work and we'll be able to find the eigenvalues. So let's see how we should choose our eigenvector for this specific example. And I'll mention before we choose a possible eigenvector that the only reason this is going to work is because the adjacency matrix is so nice. If we try to apply this to some random graph, this technique would not work at all. So let's look again for a second at our adjacency matrix. So that adjacency matrix, again, it has this first row where we have 0 and then all ones after that. And then the rest of the rows have a 1 and then all zeros after that. So rows 2, 3, 4, all the way up to n plus 1 are all the same as each other. And they're all different from row 1. Given the fact that row 1 is the only different row, and rows 2 up to n plus 1 are all the same, it's reasonable to guess the eigenvector is going to be like this. In other words, the eigenvector is going to have first entry equal to some x, we'll say, and then the rest of the entries will say that they're equal to some y. And we'll let this potential eigenvector that we're trying to solve for, we'll call it v. So v will equal the column vector x, y, 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 all the way to the end. And that vector has length of n plus 1 because we're looking at the adjacency matrix of the star k1n. So we see what happens when we multiply the adjacency matrix times that v. And we see what quantity we get in terms of x and y for each entry. So when we multiply our adjacency matrix times v, what's the first entry that we get? Well, it's going to be the dot product of the first row of the adjacency matrix with v. When we take that dot product, the x and v get zeroed out because it gets multiplied by the 0 in the first row. All of the y's get multiplied by 1 and added together. There's n of the y's because, again, v has length of n plus 1 because our matrix was an n plus 1 by n plus 1 matrix. That means that the first entry that we get when we multiply the adjacency matrix times v is going to be y plus y n times. In other words, it's an ny. So that's our first entry of the adjacency matrix times v. The second entry of the adjacency matrix times v is going to be the same as the third entry, which is going to be the same as the fourth entry and the fifth entry, all the way up to n plus first entry. So we only need to find the second entry of the adjacency matrix times v now. And we can see that the second entry, when we take the dot product of the second row with v, we get x for the first product, and then all the other products get zeroed out by the entries in that row. So the second entry and the product of the adjacency matrix in v is just going to be x. So in other words, for that product, we get the vector ny, x, 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 all the way to the end, just x's. So if we want this v, x, y, 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 all the way to the end, if we want that to be an eigenvector of the adjacency matrix, we're going to require that ny, x, 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 x is going to be a multiple of x, y, 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 y. How can that happen? How can the product of the adjacency matrix in v be a multiple of v? Well, all we need is for the ratio of ny over x to be the same as the ratio of x over y. So that is what I write in the last bullet point down here. ny over x equals x over y. We can cross multiply, which gives us x squared over y squared equals n. And that tells us that x over y equals plus or minus the square root of n. So this gives us two eigenvectors for the general form of the eigenvector that we guessed. So we guessed that our eigenvector would look like x, y, 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 y for some x and y, and we solved for the x and y, and we got two solutions. We actually got infinitely many solutions because we could take x equals square root of n, y equals 1. We could take x equals 2 square root of n, y equals 2. These will really give us the same solution because it's just going to be multiples of the same eigenvector. But the only solutions that we care about in terms of being different are solutions that are going to give us different eigenvalues. And the only different eigenvalues are going to come from different ratios between the x and the y. So the two possibilities are x over y equals square root of n, and x over y equals negative square root of n. So now that we've figured out what x over y can possibly be, we can plug it back in. So we know that x over y equals plus or minus the square root of n. And that means that the two eigenvectors for the non-zero eigenvalues are going to be non-zero multiples of the two vectors that I've written here, which I've denoted as v1, which is the square root of n, comma 1, comma 1, all the way down to the end, repeated ones. And the other vector, v2, is negative square root of n, comma 1, comma 1, all the way down to the end, full of ones. And we multiply the adjacency matrix times either of those vectors, we get the adjacency matrix times v1, just gives us the square root of n times v1. On the other hand, the adjacency matrix times v2 gives us negative square root of n times v2. So this tells us that we've found all of the eigenvalues of the adjacency matrix, because we only needed to find two more eigenvalues. We knew that all the other eigenvalues were 0, so we have found that the adjacency matrix has eigenvalue 0 with multiplicity n minus 1, and plus or minus the square root of n, each of those with multiplicity 1. So before we end this video, I'm going to give you one problem to think about. It's very closely related to the one we already did. It basically is just a generalization of it. So the question is, can you find all of the eigenvalues of the adjacency matrix of the complete bipartite graph with parts of size m and n? So you've already solved this problem when m equals 1. Now, can you see what the solution will be for any possible positive integer m? That brings us to the end of the video. Thanks very much for watching, and see you next time.